Assalamualaikum and hi everybody. I'm Eddie Elmi. In this time, I will continue with the next chapter 2.2 Quantum Mechanics. And this is the lesson I will deliver in this video. Define the term orbital and then 4 quantum number of n electron in n orbital. 4 quantum numbers are principal quantum number n, angular momentum quantum number L, magnetic quantum number M, and lastly electron spin quantum number S. In Bohr atomic model, electrons around the nucleus in circular orbit, but in reality it does not. This leads to the concept of orbital. Bohr proposed that electrons were restricted to spatial orbits around an atom's nucleus. They could jump between spatial orbits, and the energy produced by the jump caused by specific color of light observed as spectral lines. Though quantized properties were invented as but a mere mathematical trick, they explain so much that they become the founding principle of quantum mechanics. In 1924, de Broglie used the equation of Einstein's theory of special relativity to show that particles can exhibit wave-like characteristics, and that wave can exhibit particle-like characteristics. In 1927, Heisenberg made another major contribution to quantum physics. He reasoned that since matter acts as waves, some properties such as electrons, position and speed, meaning there's a limit to how well the precision of each property can be known. Heisenberg's uncertainty principle was the reason that the more precisely an electron position is known, the less precisely its speed can be known, or vice versa. The Heisenberg-Schrödinger model of the atom, in which each electron acts as a wave, sometimes referred to as a cloud, around the nucleus of an atom, replaced the Rutherford-Bohr model. In Heisenberg-Schrödinger model of atom, electrons obey a wave function and occupy orbital rather than orbits. Unlike the circular orbit of Rutherford-Bohr model, atomic orbitals have a variety shape ranging from sphere to dumbbell to cloverleaf. Erwin Schrödinger introduced quantum mechanics to solve the problem of finding electrons and the energy states of the electron in an atom. In quantum mechanics, an electron can be found in a region of space known as orbital. Electron density is a probability that an electron will be found in a particular region of an atom. Also, electron density can be pictured as electron cloud. The higher the electron density, the higher the probability that an electron may be found in that region. An atom may contain more than one orbitals. These orbitals distinguish from one another on the basis of their size, shape, and orientation in space. These parameters are expressed in terms of different numbers called quantum numbers. Quantum numbers may be defined as a set of 4 numbers, which we can get complete information about all the electrons in an atom. It tells us the address of the electron, such as size and energy of orbitals, orbital shape and orbital orientation, and motion of electron. First quantum number, principal quantum number n. It tells the main shell in which the electron resides, energy of that particular electron, the approximate distance of the electron from the nucleus. The value of n is positive integer. As n value increase, energy level increase, orbital size larger. Principal quantum number also tells the maximum number of electrons that a shell can accommodate is 2n powered by 2. It means that only 2 electrons occupy at first energy level, 8 electrons at second energy level, 18 electrons at third energy level, and so on. Second quantum number is angular momentum quantum number, denoted as L. also known as azimuthal or subsidiary or orbital quantum number. The value of angular momentum quantum number is determined by the value of principal quantum number. The value of angular momentum quantum number is integer starting from 0 to the value of principal quantum number minus 1. The number of angular momentum quantum number tells the shape of orbital. When angular momentum quantum number is 0, it is orbital S with spherical shape. When angular momentum quantum number is 1, it is p orbital with dumbbell shape. And if angular momentum quantum number is 2, it is d orbital with cloverleaf shape. Thus, the angular momentum quantum number is dependent on principal quantum number, so that the angular momentum quantum number is integer starting from 0 and less than principal quantum number. Let's we have example about principal quantum number, angular momentum quantum number, and the shape of orbital. For principal quantum number 1, the integer less than 1 is only 0. For principal quantum number is 2, the integer between 0 and less than 2 is 0 and 1. When principal quantum number is 3, the integer between 0 and 3 is 0, 1 and 2. Let's determine the shape of orbital from angular momentum quantum number. For angular momentum quantum number is 0, this is the s orbital with the sphere shape. For angular momentum quantum number 1, this is p orbital with the shape dumbbell. And lastly, for angular momentum quantum number 2, this is d orbital with the shape clover leaf. The third quantum number is magnetic quantum number. Magnetic quantum number indicate orientation of orbital in the space around the nucleus. Magnetic quantum number integer from negative azimuthal quantum number to the 0 and to the positive azimuthal quantum number. The value of magnetic quantum number is determined by azimuthal quantum number. The number of possible magnetic quantum number values is 2 times azimuthal quantum number value plus 1. Let's we have an exercise about the value of magnetic quantum number and the number of possible magnetic quantum number values. When azimuthal quantum number is 0, the magnetic quantum number value only 0. Insert 0 into this equation, only one possible m values. It means that only one orbital for azimuthal quantum number 0 and magnetic quantum number 0. Since azimuthal quantum number is 0, this is s orbital. Next, when azimuthal quantum number is 1, magnetic quantum number is integer from negative 1, 0 to positive 1. Insert 1 into this equation, we get 3 possible magnetic quantum number values. Thus, for angular momentum quantum number 1, it has 3 orbitals. Since angular momentum quantum number is 1, this is p orbitals. Next, azimuthal quantum number 2, magnetic quantum number start from negative 2, negative 1, 0, positive 1, positive 2. Insert 2 into this equation, we get 5 orbitals. Since azimuthal quantum number is 2, the subshell is d orbital. This is hierarchical relationship between 3 quantum number. Principal quantum number limits the azimuthal quantum number, and then azimuthal quantum number limits the magnetic quantum number. Let we have example to show principal quantum number limit the azimuthal quantum number. If principal quantum number is 2, the only azimuthal quantum number is 0 and 1. Next example show azimuthal quantum number limit magnetic quantum number. For azimuthal quantum number 1, the only magnetic quantum number values is -1, 0 and +1. For azimuthal quantum number 0, the possible magnetic quantum number values only 0. This diagram summarizes hierarchical relationship between principal quantum number, angular momentum quantum number, and magnetic quantum number. For principal quantum number 1, 0 is the value for angular momentum quantum number and magnetic quantum number. For principal quantum number 2, angular momentum quantum number is 0 and 1. Magnetic quantum number 0 for angular momentum quantum number 0. For angular momentum quantum number 1, it has 3 magnetic quantum number, which is -1, 0 and +1. For principal quantum number 3, it has 3 angular momentum quantum number, which is 0, 1 and 2. For angular momentum quantum number 0, magnetic quantum number also 0. For angular momentum quantum number 1, it has 3 magnetic quantum number, which is -1, 0 and +1. For angular momentum quantum number 2, it has 5 magnetic quantum number, which is -2, -1, 0, +1 and +2. The last quantum number is electron spin quantum number S. The value of electron spin quantum numbers determine the direction of spinning motion of an electron on its own axis. The electron spin quantum number has 2 values, either positive half or negative half. 2 possible motions of an electron, clockwise and anti-clockwise. Set of 4 quantum numbers used to describe each electron in an atom. A set of 4 quantum numbers consists of principal quantum number, azimuthal quantum number, magnetic quantum number, and electron spin quantum number. Principal quantum number, azimuthal quantum number, and magnetic quantum number describe orbital occupied by electron, while electron spin quantum number describe electron spin on its own axis. These 4 quantum numbers are written begin with orbital size, orbital shape, then orbital orientation, and lastly electron spin direction. So in bracket it begins with shell, then subshell, after that orbital, and lastly electron spin. Let's we have an example how to write quantum set. Take hydrogen atom in orbital 1s as first example. This number 1 represents principal quantum number 1. Azimuthal quantum number 0 represents s orbital. Since azimuthal quantum number is 0, only 0 is allowed for magnetic quantum number. Electron spin quantum number either positive half or negative half. Note that by convention, we assign first electron is positive half. Another example, give one set of possible quantum number for an electron in 2p orbitals. Number 2 in 2p orbital means principal quantum number is 2. P orbitals mean azimuthal quantum number is 1. Thus, magnetic quantum number is positive 1. Take the electron spin quantum number positive half first, or the next set of possible quantum number has similar principal quantum number, azimuthal quantum number, and magnetic quantum number, but different electron spin quantum number, which is negative half. Or we have the third set of possible quantum number. The third possible quantum number, it has similar principal quantum number 2 and azimuthal quantum number 1. But magnetic quantum number is 0. Electron spin quantum number is positive half. Or the fourth possible quantum number, it has similar principal quantum number 2, azimuthal quantum number 1 and magnetic quantum number 0, but different electron spin quantum number, which is negative half. Or we have the fifth possible quantum number, which has similar principal quantum number 2, azimuthal quantum number 1, but magnetic quantum number is negative 1. Electron spin quantum number is positive half. Or we have the last possible quantum numbers. This possible quantum number, it has principal quantum number 2, azimuthal quantum number 1 and magnetic quantum number negative 1. Electron spin quantum number is negative half. I choose example 8 to continue our discussion. Write the 4 quantum numbers for n electron in a 2p and 3d orbitals. Let's rewrite the 4 quantum numbers for n electron in a 2p orbitals first. The principal quantum number for 2p orbital is 2. Azimuthal quantum number is 1 because this is p orbital. For azimuthal quantum number 1, magnetic quantum number allowed is negative 1, 0 and positive 1. Electron spin quantum number either negative half or positive half. So 2 electrons for each magnetic quantum number negative 1, 0 and positive 1. 2 electrons times 3 value of magnetic quantum number. Thus we have 6 possible ways of quantum numbers. So these are 6 possible ways. First one, n is 2, L is 1, M is negative 1, S is positive half. Second one is n 2, L equal to 1, M is negative 1 and S negative half. The third one is n equal to 2, L equal to the 1, M equal to the 0 and S positive half. The fourth one is n equal to the 2, L to the equal to the 1, M equal to the 0 and S equal to the negative half. The fifth one is n equal to the 2, L equal to the 1, M equal to positive 1 and S equal to the positive half. And the last one is n equal to the 2, L equal to the 1, M equal to the positive 1 and S equal to the negative half. Let's continue. Determine 4 quantum numbers for an electron in 3d orbitals. Principal quantum number and azimuthal quantum number for 3d orbital is 3 and 2 respectively. When azimuthal quantum number 2, the possible magnetic quantum number is negative 2, negative 1, 0, positive 1 and positive 2. Electron spin quantum number either negative half or positive half. So 2 electrons at each 5 orbitals, so it has 10 possible ways for quantum numbers. So this is 10 possible ways set of 4 quantum numbers. So take your time to see these 10 possible 4 quantum numbers. That's all for this session. Our next video, I will teach you how to sketch the 3D shapes of S, P and D orbitals. Thanks for watching. See you around.